Okay guys, welcome back. I hope you're enjoying the series. Like and subscribe if you are. So we've got our function now to pixelate. I'm actually going to do a quick update to this, so follow along with me. I actually do want to be able to tell it exactly how many pixels I want. I just want to make this function a little bit robust. So we're going to add an optional size parameter, and we're going to set the default of that to none. And I'm going to quickly add another parameter here, and this is going to take a tuple, and this will be let me delete this, so we'll say the size in pixels as a tuple, just to make this quick here. And we're going to make one change to our code. If we pass in size, so if this size exists, we can actually use the none as a way to check for false. None will evaluate to false. So we can say if size, then we want to calculate our image low res in a different way. So, and if we don't pass that in, which is the default, then it'll use a scale ratio. So this is going to be the default operation, if you will, is going to be to use a 5% scale. But if we pass in a size, then it's going to use that. It's going to override that. So in that case, we don't need this fx, fy, and we'll put in size 0 and size 1. That's going to be our tuple that we pass in. Okay, so, and the reason I'm doing that is I actually want to scale my Mario image way down. So if I keep it as is and if I run it, it's not going to have any impact because by default that's none. So if I go to my test.jpg, I still have this Mario here. But what I want to do is just for today, when we start talking about colors, I'm going to shrink this down super far. So instead of giving it a scale ratio, now I can give it a size as a tuple, and I'll give it a 1 by 1. So I'm just going to have 1 pixel. Now I know that sounds kind of weird, but I want to do that only because I thought it would be nice if we could look at 1 pixel. Oops, output.png. So now I have just 1 pixel. So if I were to take the entire Mario image and shrink it down to 1 pixel, this is what it came up with. Maybe we could do a 3 by 3, so it's a little bit easier to see. And here's my output. So that's the entire Mario image shrunk down to a 3 by 3. So we've got a few different colors. And the reason I'm doing this is I want to introduce the color matching now. And instead of looking at lots of pixels and getting confused, I thought it'd be nice if we could just look at a couple of colors at a time. So maybe we'll just look at this 3 by 3. So we've got some blues, some grays, some skin tones. We got the the nice Mario hat red. So this must be Mario's head, shrunk down to 1 pixel. So the next step in our operation now is we want to be able to match the colors to our Lego default colors. So let's think about how we are going to do that. So what we have is a color in the value of RGB, and we have these pixel values here which are colors. So the question is, I'm going to go back to 1 by 1 just to make this simple. So again, if I go to 1 by 1, now I just have this 1 pixel, this little peach pixel here. Mario's been shrunk down to a single pixel. So let's look at actually what this data looks like inside of, so I'm going to comment out this code here. And so now I have a matrix object, but the matrix only has a single pixel. So this will be a little bit easier for us to look at. So let's actually print out our image low res into the console, and let's see what the data looks like. Okay, and you can see the data is, it's a list like object, which contains a list, which contains another list. So let's break it down. What do we see here? So if you think about it, a pixel in RGB color space is made up of 3 parameters, RGB, or actually in our case, it's BGR. So as we get started here, I want to tell you about one of the nuances of working with OpenCV. OpenCV actually uses BGR color space. Now don't panic, it's not complicated. It's exactly the same as RGB color space. except the blue channel is the first channel and the red is the last channel. So you can imagine you have the exact same data, but you flip-flopped the front and last number, and the green is still in the middle. And the reason is that there's some historical reasons for why that is, and the point is don't get too caught up on that. It's not difficult. The data is essentially the same. It's just the last number and the first number have been reversed if you are comparing an RGB and a BGR number. So let's take a look at our data again here a little bit more closely. So in the absolute middle, we have a list of 3 numbers, and those 3 numbers are our B, G, and R. So we have a B value, blue, of 121. We have a G value of 150, and we have a R value of 214. So that is our BGR. Now, if I were to convert this to RGB, I would use 214 for R, 150 for green, and 121 for blue. So again, the same numbers, just in the reverse order. Now so we have a list here. This is a pixel, right? A pixel consisting of 3 objects, the red, the green, and the blue layer. That's a single pixel. So why is that in a list, which is in another list? Well, an image is made up of rows and columns. So what we have is a row. So each pixel is in a row, and a row is, you can think of a row as a list of pixels. So now we have a row of just 1 pixel. So this is the complete row. And then those rows are put into a list stacked on top of each other, and that creates an outside list. So maybe this will be a little bit more clear if we look at this in a 3x3 again. Let's look at this again, and let's print it out. And now you can see that we have a 3x3. So we have our first row, which consists of 3 pixels, pixel 1, pixel 2, pixel 3. So those are the top 3 pixels of the image. Okay, and we can actually probably visually inspect that. Oops, I didn't write it out, so let me write it out again so we can look at it at the same time. Okay, so let's look at this top row, which is represented by the data right here. So it's pretty obvious that this middle pixel here is red, so that's going to have a very high red value. Now if you remember, RGB is backwards. This is not RGB, this is BGR. And you can see in fact that this middle pixel here, which corresponds to 0, 1, 2, so 0, 1, 2, this has an extremely high red value, very low other values. So that's our red pixel right in the middle there. Similarly, this one is mostly blue over here, so we have an 82, a 30, and a 0, so BGR. No red, lots of blue. So you can see that this is the top row. So this is pixel number 0, 0, 1, 1, pixel number 2, 2. And then, as I mentioned, this is an entire row object, and this is inside of a bigger list which makes up all the rows. So each row, so this is row number 0, which is the top row. Then we have row number 1, which is 1 down, so 1. And row number 2, 2. So this is the data representation of our 3x3 image. And what we need to do is we need to figure out a way to take the data of our image and compare it to a pixel, the pixel color, and compare it to a Lego block color and figure out what Lego block is the best Lego block to put in that spot. So let's use this red Lego, this red position just as an example for our discussion. So if we were looking for a red Lego block to put into that position, let's go back to our code now. We would look at all of our Lego blocks. Okay, our value is right here. We would look at all of our Lego blocks, whoops, and we would try to figure out which Lego block looks the most red. And just like the data on an image, the one that we can expect to look the most red is going to have the highest red value and probably small B and G values. So just by using my visual inspection, if I look at this, I might say, oh, this block has a very high red value. Remember, now we're RGB. I've put these in as RGB objects because that's more standardized outside of OpenCV, let's say. And I might say, okay, this has a very high red value. But then if I compare these two, I say, oh, it also has a very high G and a very high B. So that might not be the best block. Let's look again. Then I come down to here and I see, okay, this has a high red. That's a good start. And I see that the G and the B are also pretty low. Percentage-wise, these are pretty low. So this is probably a pretty good match for this block. And if I look at this, it's a bright red block. So of course, we're not going to just look at the numbers and try to make a guess. We're going to create a function now that is going to do that for us. But essentially, that's what we want to do. We want to treat this like an object in three-dimensional space. You can think of red, green, and blue as X, Y, and Z, or you can think of them as length, width, and height. You can think of this as a three-dimensional space. And we want to find the block that has the closest distance to the location of our actual pixel color in that space. Okay, so to find the difference between 2 points in space, we want to calculate what's called the magnitude. And to do that, we calculate the distance, the difference in the X, Y, and Z direction. We square those, we sum those, and then we take the square root. So let's actually create our function. And let's call this magnitude. You can think of this as a general utility that can be used to calculate the magnitude of a vector. And we will provide this with 2 list objects. So we're going to have list 1, and this will be a list type object, and list 2, this will also be a list type object. And this will return a float value, which represents the magnitude of the vector between these 2 points, if you think of them as points. Again, the concept of a color as a point in space is kind of a conceptual idea. You can also just think of these as the difference in red, the difference in blue, and the difference in green. That's another way to think about it. But visually, you can think of it as a point in 3D space. So what we want to do is we want to take a difference, we'll say dr, this is our difference in red, and let's assume that let's actually make some notes so that we know what we're doing here. So this will be, calculates the magnitude of a color vector, let's say, in RGB space. Okay, and we have our parameters, and we have list 1, which is a list, and this is a RGB values, and we have oops. Let's move this over, and we have list 2, which are going to be RGB values, and then this will return the magnitude as a float. Okay, that's pretty easy to understand. So it's very important that we make sure we have our planning here. This is where the documentation comes in. If these are both going to be RGB values, we want to make sure we're accessing the correct parts of the array. So the R value is going to be the 0th location in that list. So our dr is going to be list 1. We want to access the 0th, and we want to subtract list 2, 0. Now you might be wondering, what if list 1 is negative or something? You know, in RGB space we shouldn't have that issue, but we could get a negative result. For example, we could have list 2 being bigger than list 1. We have a negative number. That's okay, because we are going to square these values in our calculation. Once we square them, the negative sign is no longer relevant. and we have DG, so we're going to do the same thing. I'll tell you what, I'm just going to quickly pull this code down. So we have DG and DB. So we have our RGB deltas, and we're going to use the first and the second index to get those values, okay? And now we want to return the magnitude. So to return the magnitude, we're going to return, and the first thing we want to do is we want to take our dr and square it. So we'll do dr times dr plus dg times dg plus dB times dB. So this is going to be the sum of the squares of the deltas in R, G, and B space. And you might be wondering, why am I using dr times dr instead of dr exponential 2? I can do both. Both are fine. I think that the multiplication is a little bit faster than using an exponent, but it probably doesn't matter whatsoever. So feel free to do that. If you want to do dr squared, that's absolutely fine as well. And then I'll tell you what, we'll use that now. So we're going to take this sum, and then we need to take the square root. So what I will do is I will just put that to the 0.5 exponent. That's the same as taking the square root. So we're going to return that value. Okay, so this function will take in a color. Let's call this color, let's make this specific to our program, just so it's very clear. So we have color 1 and color 2. And we'll just call this color difference. I just want to make this more clear what the purpose of this function is in the context of this program for you guys. Okay, so we're gonna calculate the color difference. It's gonna have two colors. They're gonna be a list. It could also be a tuple. And we are gonna subtract those two values in R, G, and B space, and then calculate the square root of the sum of the squares. And that will return the distance between those two values. Okay? So next what we need to do, now that we have our color difference function, we need to iterate through our RGB default colors here and find the best match. Okay, so let's do this. Let's create another function, and we'll say define best color match. And we're going to pass in an RGB value. So this will be our color, which is again going to be a list. And this is going to return a tuple. And the tuple it's going to return is the best color. So if this was the best color, let's say white, it should return all the information about that color. That's what I'm expecting it to return. Okay? So this function is just going to take one color because it's going to use our color palette. Actually, if we want to have a custom color palette, we may want to specify that now. So we'll say palette. This is the available colors, and this is a list object. And we're going to set this default equal to our default colors. So if we don't provide a palette, it's going to use our default palette. If we want to provide this particular palette, we could provide a special list of objects. So we're going to do that now. So that'll be a nice feature to have later. Okay, so here's what we're going to do. First, we're going to initialize our best color to none because obviously we haven't found our best color yet. And what we're going to do is we're going to iterate through our colors here and try to find the best color. So we're going to say for color in palette. We don't want to use color. We'll say for P in palette because we already have the color here as an argument. So for P in our palette, so we'll say our palette color is P. We want to perform the color difference calculation. So we're going to provide the color difference. We'll say D, the difference, is equal to the color difference and we're going to put in color 1, which is going to be our color that we provided to this function, and color 2 is going to be P3, or sorry, P2. Now why is it P2? Because we're going to pass in our colors in the form of a tuple, and 0, 1, 2. So index number 2, which is the third object, is going to be the tuple of our RG and B value, okay? Now we have a problem here. The problem is that, as I mentioned, the color that we're working with is in BGR. So we have two options. One is we could adjust for that now in our best color match. Another is we could, outside of this function, convert it to RGB and then pass it in as an RGB value. So then this function would be valid. I think that is a better option, because if this function is performing two operations, if it's converting a color to a different color type and finding a match, then it might be confusing to an end user what it does. So we're going to actually rename this. We're going to call this color RGB. So we know we have to pass in an RGB color. That way we know we have to convert a BGR value to an RGB before it goes into this function. And let's also create our minimum D is equal to none. Okay. Minimum delta, minimum difference is none, because we haven't found anything yet. So what we're going to do is we're going to loop through these colors. So for P in palette, we're going to find the delta D between our color that we provided and the color of this block as we iterate through. And we're going to calculate D. And we're going to say if minimum D is none, so if D is less than minimum D. Now the reason I want it, oops, I don't need an if there, or D is less than minimum D. Now the reason I'm doing this first is I can't compare D to a value that doesn't exist yet. And I also don't know what a good value is to put in there. I could put in, one way to solve that is I could put in a super, super high maximum value that it could never achieve, and it would always be, the first iteration would always be less than that. But I think saying D is none is more explicit as to the fact that it hasn't been found yet. So this is a little bit more clear, in my opinion, than doing the other method. So if minimum D is none, then we're going to do this. Or if this is a better match, if our delta is less than the minimum delta that we found before, then that means that this is a better color match. And if that's the case, then we want to set our minimum D equal to the current D, because that's now our best delta. And our best color is going to equal this current color P. And then finally, after this is done, we want to return P. This is our best color. So let's test this out. And we have our 3x3 image here. So we're going to say for row in image, because remember this image is essentially a stack of rows. And we could say for pixel in row. So we're kind of doing a double loop here. First, we're going to loop through each row in the image. And then each row is composed of a pixel. So we have the first row, which has 3 pixels. For each pixel, we want to find our best match and print it, let's say. So we'll say print, let's see here, best color match is what we called it. Best color match, and we want to put in our pixel as data. Now I'm going to run this and let's see if our code works. So there you go. Looks like all of them map to medium lavender. So there's a bug in our code somewhere, and if you remember, one of the problems that we have, I'm sure, and I hope you caught this already, is our pixel is in BGR instead of RGB. So we can actually create an RGB pixel for comparison purposes and say that that is equal to, we can make this a tuple since it's not going to be modified. So this is pixel 2, pixel index 1, pixel index 0. So that's backwards. We could have reversed it or something else. You could have done some operation. But now we have an RGB pixel that we can pass in. So now we have RGB to RGB. That's good. And it looks like we still have a bug, so I don't know what it is. Let's try to diagnose it together. It looks like it's always finding medium lavender, so there must be a bug in the code. Let's take a look at it, see what that is. Oh, sorry. So I realize what the problem is. The problem is we're returning P, which happens to be the last P in the list. We should be returning our best color. So we were returning, we were not returning our best color. So that's our error. So let's run this again. And let me turn that off. Okay, so let's take a look at our image and let's compare. Let's see if our results are making sense. So our first block, it looks like it said dark stone gray, so that probably makes sense. The next one it says is a bright red. That looks good. Next, earth blue. That probably makes sense. Now we have medium lilac, so that might seem strange, but this does have a purplish hue to it. Yellow, okay, that could make sense. Blue makes sense. Blue makes sense. Blue makes sense. And then orange. So it looks like it is working properly. We are getting our closest pixel matches now. So I'm going to end this now. So you can play around with this. You can play around with different pixel values. But this shows how we can take our image data and we can convert it into the closest matching color in RGB space. Thanks.